So today I want to do, in our little webinar, I want to talk about signal processing, but this time for EVs, electric vehicles. So I want to introduce a bit of maths really, because you should be finding in GlyphWorks coming soon some new capabilities for EVs. And I want to introduce to some of the maths behind them so that you feel comfortable with that and hopefully a little bit enlightened about things that GlyphWorks can do. So just before we start, obviously, the first thing is just for people who are new to Proncea, then Proncea is a brand which has two software products. There's nCode, which is durability analysis, and ReliaSoft. As well as the software, though, we also do lots of training and education, and this webinar really is part of that training scheme. It's a theory review on AC power analysis. And of course, we also have services as well. And one that's close to my heart, as it's in the office I work, is materials testing, where we do fatigue testing of different materials and structures there. In terms of software, which is really what we're talking about today, there are those two brands, ReliaSoft, which is all about reliability analysis, and there's nCode, which is about durability analysis. And today, we're concentrating on the digital signal processing part on that, and that's going to be GlyphWorks. Okay, so I want to talk about signal processing of EVs, electric vehicles. And in particular, the bit that we're trying to address here is to improve the efficiency of EVs and to measure the losses and things like that. So in an electric vehicle, there's a transfer of energy from one state to another. We've got DC voltage in a battery. That gets converted through an inverter to AC, which drives a motor. That drives a gearbox, which is mechanical power, and that transfers to kinetic energy for the whole vehicle. And as we know, every time we convert energy from one form to another, we get a loss. And it's important to understand that loss and to see if we can do something about it to make it more efficient. So in the new version of GlyphWorks, which you'll be seeing, there's new features to do efficiency maps. And these look really quite beautiful, actually. My colleague Tudor was showing me a flow just before we started this with an efficiency map, looking at the efficiency from DC through to the AC inverter, through to the transmission, and of course with the whole vehicle as well. Now, the bit that I want to be concentrating on mostly, though, in this particular webinar is that inverter, the bit that converts from DC to AC in order to drive the motor. It's that bit that we want to see if we can get to be more and more optimized, to get more power from it. So when we look at this little shift of energy from one format to another, we can see some of the maths is really easy in GlyphWorks. When you look at DC power, then power is just voltage times current. And that's really easily done in GlyphWorks, well, really since it was created about 15 years ago. They're a very simple calculation. And mechanical power is just as easy too. It's just torque times speed. So again, if you've got the torque in a shaft, you know it's speed. We can multiply those together using a nice multiplication glyph, and we've got mechanical power. And as I say, what's coming out in the next version is you'll be able to take those two as input, and we can produce those nice plots we saw on the previous slide, which is efficiency as well. Even kinetic power, despite the fact the maths looks a bit more complicated, anyone who's been using the GPS glyph in GlyphWorks knows that through GPS data alone, we've got a pretty good way of estimating the kinetic power of the entire vehicle too. So again, looking at the efficiency loss is quite straightforward in GlyphWorks land. Now, when I came to this, I thought, being a mechanical engineer, well, AC is going to be easy as well. We've been doing it, after all, for years and years. So our cousins in the electrical engineering side, they're used to dealing with AC on power grids. And they've got a nice sinusoidal waveform. And electronics engineers, they talk about the concepts of active and reactive power. And they're defined really as active reactive power is that that's consumed by a resistive load on the network, so lights, motors, heating systems, and so on. And they also have this concept of reactive power. Now, reactive power is not real power. It's actually an out-of-phase component. So as the sine wave goes back onto the grid, it's slightly out of phase, and that effectively negates power. So it's not being consumed, but it's just that out-of-phase bit that negates power, and that can lead to grid instabilities and things like that. So, okay, it's not being used, but it has a detrimental effect, and the electronics engineers want to measure that in order to charge for it. Now, with the EV power, the electric vehicles, we see that the waveform is non-sinusoidal, and it's not constant either. It's varying all the time in amplitude and frequency. But EV engineers are also interested in active and reactive power. That active power is consumed to drive the vehicle along. It's doing real work, shifting all of that weight. But we're also interested in reactive power. It's not consumed, but it does cause efficiency losses. And so we want to minimize those efficiency losses. So what we want then from digital signal processing are two measurements. We want an accurate measurement of active power because that's the one we want to maximize, because that's the bit that's doing us real work. And we want a robust inference of reactive power because that's the parameter we want to minimize, because that's creating efficiency losses. Now, the astute of you here will realize that why did he use accurate measurement in item 1 and robust inference in item 2? Well, that's purely on account that reactive power isn't real. It's not something that's consumed. We can't easily measure it, if you like. It's a mathematical thing. But we need to make sure that we've got a robust way of calculating it so that it's not affected by the mathematics. It's got to be a parameter which is robust so we can minimize it. So, in this next sort of about 40-45 minutes, I want to talk about, first of all, the definitions for AC power. So, we'll go back to the power lines where it's nice and sinusoidal. We're going to have a look at what active, reactive, apparent power, and the power factor is. And then we're going to have a look at the analytical and digital signal definitions of those. So, a little bit of a revision, if you like, from when we were back at university days. And then we're going to move on to EVs. So we're going to have a look here at the inverters in electric vehicles. We're going to look at two different methods of calculating these parameters. We're looking at time averaging methods and instantaneous measurements as well. And in both cases, we're going to look at a time domain and a frequency domain method. And we're going to sum up which ones we think are best in which cases. And then we're going to show a GlyphWorks post-processing case study so you can see how it can be implemented and how we can actually get value from GlyphWorks. Okay, so let's go back to a little definition, back to our university days, and think about what is AC power. So on this, I've demonstrated this by looking at AC power is just voltage times current at an instance. And here I've got, you notice here, I've denoted my instantaneous voltage, U at T, as capital U cos omega T. So my definition here is U is the amplitude of the voltage, and correspondingly I is the amplitude of the current. Now, I know electronics engineers might prefer that to be amplitude over root 2, so the RMS, but for this sake, I'm using the classical mathematical definition where U is the amplitude and I is. And of course, the current IT is the amplitude I times cos omega T, and I've introduced a phase angle here, a phase lag between the current and the voltage, and we'll see what that does here. So when there's no phase lag, when they're both completely in phase, we can see here, there's the voltage in blue and the current in orange here. When we multiply them together, the power comes out of this dotted green line. So the first thing we need to notice is that instantaneous power is sinusoidal, and it's at twice the frequency of the input current and voltage. Another thing we notice is that it's always positive as well, because a negative times a negative is also a positive. So if I want to calculate the energy that's the area under this power, I've got positive energy, and that's called the resistive load. It's the energy which is, in our case, driving our car. Now, what happens if the current is offset by 90 degrees? So now what we get is we've got to still see here the voltage and the current, same amplitude, same frequencies, but we now notice that the current's been offset by 90 degrees. So now when we multiply them together, we still notice that we've got a power. The power's got the same amplitude and frequency as before, but now it's got a zero mean. So if we take the area under this, you'll find we've got negative energy as well, or negative power. Well, what does this mean in practice? Well, it's not real. What it sort of means, if you think about the old water pipe analogy of voltage and current, what we've got is we've got water being shifted one way and then sucked back. So the water's still moving, it's still doing energy, but it's not actually driving anything, a real load. So what it's doing is it's creating heat, and that heat is creating efficiency losses. So this is what we call a reactive power component. It's not doing physical work. The area of this in the end is zero, but it's still creating those efficiency losses. Of course, in real life, it's somewhere between the two, isn't it? This phi is not even 90 degrees. And so when we multiply them together, you see, in most cases, we end up with some active and some reactive power here. So let's add a little bit of maths, because I like to add a bit of maths to this. But don't worry, because nothing actually exceeds sort of high school maths at this level. So let's have a look, first of all, at our voltage and current. When we multiply them together, remember power is instantaneous voltage times instantaneous current. So that's now U cos omega t times I cos omega t. Bit of simplification there, UI cos squared omega t. And if we remember back to those double angle formulas and all that posh stuff there, we find this comes down to this equation here. So the UI over 2 is the amplitude. So this is the apparent amplitude here. We call that the apparent power. It's the amplitude of the power signal. And that's multiplied by cos 2 omega t. So remember, that's where the twice frequency component comes in, plus 1. And that plus 1, that's what makes it positive. So it's always going to be positive. Now, of course, if the current and voltage are offset by 90 degrees, this now becomes U cos omega t times I sine omega t, because the sine is 90 degrees offset to the cosine. And again, using a bit of high school maths, when we multiply this out, we've got our UI over 2, so the same apparent power. We've got the same frequency, 2 omega t. But this time, being a sine wave, of course, the power has equal positive and negative, and that's why we've got that reactive power. A little bit more general case now. If we've got an arbitrary phase angle at phi, when we multiply these together, again using a bit of high school maths, we'll notice that the amplitude, ui over 2, is the same. So this amplitude here, the apparent power is the same. But now we've got this cos 2 omega t. So again, it's the same frequency, 2 omega t. But this time we've got this constant term, cos phi. And this ui over 2 cos phi is the mean level of this power coming out. We call this cos phi the power factor. So when cos phi is equal to 1, and the power factor is 1, then everything is active. If that was equal to 0, so cos phi is 0, then everything is reactive. So the power factor is a value which changes between +1 and -1, and it tells us how much active and reactive component we've got in the system. Right, let's tidy up the board a bit, and let's expand this equation here a little bit more, again, just using high school maths. So if we expand this now, we now get the cos 2 omega t times cos phi, plus sine 2 omega t times sine phi, plus our cos phi terms. And if we now group them together, what we find is that actually the power is the weighted sum of the active component plus the reactive component. So we've got some definitions here. the total instantaneous power at any point, the amplitude of it, we can take as being the active power, which is ui over 2 cos phi. The reactive power is ui over 2 sine phi, so these are amplitudes. Of course, if we take if we want to find out the apparent power, which is ui over 2, we can effectively take the vector sum of these. Now, I'm not saying that power is a vector quantity, it's still a scalar, but this triangle enables us to think about it and remember the equation, really. So this is now giving us the apparent power, and of course the power factor, which is the P over S. So this, if you like, is our definitions, our classical definitions of AC power in terms of active, reactive, apparent, and power factor. Now, these are all right. But when we're dealing with our electric vehicles and even the mains, we don't have nice sinusoidal waves that we can tap into a computer. Very often we have digital data. So over the years, the engineers have come up with a digital definition as well. So the active power is usually defined as the average instantaneous current and voltage over a fixed period of time. So this period has to be integer multiples of the half sine frequency. So you can have a half wavelength or a full wavelength or 1.5 wavelengths, but you can't have 1.333 wavelengths because otherwise some negative bits will offset some of the positive bits. So it has to be direct multiples of that half cycle. But again, if you look at this, if we take the average of u pi over that time, and we end up with the same equation. So that's why it works. We get the same definition. Of course, with the apparent power, again, we're used to this right from being at high school, that if we take the RMS of the voltage times the RMS of the current, that gives us the apparent power. And again, we can look at this mathematically because it follows this neat little trick here. If I take the RMS of any sinusoidal wave with an arbitrary frequency offset, what happens is that frequency offset just disappears. So I now get, in this case, I over root 2. So when I multiply the RMS of voltage together, I get ui over 2. So I get the same equation here, and that's why the digital definition works. And of course, in the reactive power, then we can take, again, using that power triangle as a way of memorizing this, we can take the sum of the squares of those, or the difference of those, and this will then give us the ui over 2 sine phi, which was our original definition. So if we've got a nice mains system with pure sine waves, all of constant frequency and amplitude, that's the way to do it. But what's different then about our inverter? So if we look at a typical inverter signal, so these were done in Glyphworks, so we can see this is now the current. It looks almost sinusoidal, doesn't it? But look at the voltage. Now the voltage doesn't look sinusoidal because it's using power electronics in the inverter. So it's actually using a pulse width modulated square wave, if you like, to generate something in voltage. So when we filter it and everything, we can get the current that we want. So now if we're to multiply these together, the instantaneous voltage times the instantaneous current, I don't get a smooth sine wave. I end up with this very jagged profile here. Of course, we could still work out the active, apparent, and reactive power in the same way as we did before. So if I take the average of the voltage times the current over a half cycle interval here, I get 182.5 watts. Similarly, if I take the RMS level of this, multiplied by the RMS level of that, my apparent power comes out at 268. We call these, although we normally think of them as watts, I actually call them volt amps. So it's still a power, but we use VA in order to differentiate it from active power, which is W. And then, of course, we use our power triangle to work out the reactive power, and this comes out now to 196. And we use VAR for volt amps reactive, so that by the units we can tell what we're looking at. Now, when we look at this, it looks a little bit fishy, because we're used to seeing reactive power as the type when it goes negative. But here, when we look at it, we can see we should have a lot more active power than we do reactive. But these numbers quite clearly show the other way around. They are showing that we have more reactive power than active. So what's happened here? Well, the active power is correct by definition. There's no problem with that. It's the apparent power and thence the reactive power which is the problem. And the reason is, it's because this consists, our voltage here consists of lots of harmonics, all at different frequencies. And we've smudged them all together to create one single RMS value. And then we've multiplied that by the RMS here, which this one is almost one pure sine wave. So the problem is that we've squidged all the frequencies and mixed them together. We've not kept them separately. And that's why we've got this apparent anomaly in these values. So let's have a look at another definition that we can use for non-sinusoidal voltages and currents like we find in inverters. So for that, we need to keep the frequencies separate all along. So we're going to use a Fourier transform for that. So if you remember, a Fourier transform works like a mathematical prism. We know if we shine a light into a prism, the prism diffracts that light out, and we can measure the different colours or wavelengths or frequencies. And by looking at the intensity of those, we've got an idea of how the colour spectrum of light works. Well, a Fourier transform is exactly the same with maths. If we shine our time history of voltage through our mathematical prism, then it gives us what we call the power spectral density function. So this is a plot of the mean squared amplitude here at each frequency. Frequencies on the x-axis here, mean squared amplitude on the y-axis. And if we take the area under any part of this PSD, that gives, and square root it, that gives us the RMS. And that, remember, is part of the definition of the traditional power. So this gives us the RMS with respect to frequency, and it keeps the frequencies separate for us. So in the frequency domain, we can also calculate the power. So in this case, here's our current and here's our voltage. If we look at the PSD of those, we can start to see this is the PSD of the current here. This is the PSD of voltage that we're getting here. Now, if I was to take the square root of this, multiplied by the square root of that now gives me my apparent power. So now, if I were to do that, I can get my power spectrum here, and I can simply take the area under that, and now, hey presto, I end up with 185.39 volt amps. Now that means that my reactive power is a lot smaller. This 32 is a lot more like what we would expect. So what's actually happened there? Why has that happened? Well, as we notice, even though the voltage is made up of all of these harmonics at these high frequencies coming in, these harmonics in voltage are about the same order of magnitude as our principal frequency coming in here. Yet, when we're looking at the current, most of these high frequencies have been damped out. They've been sort of lost through capacitance and things. And these are now 4 orders of magnitude less. So although there are still frequencies here, they're much lower. So when I multiply them together, then I end up with a very small number here. And that's why it tends to be very different if I smudge them all together to start with. So what we notice with a power inverter is we've got this spectral gap in the middle. So on the left, we have the fundamental frequency of our AC system. And on the right, we have the switching harmonics, and we have this gap in between. So what happens if we were to filter out those harmonics? So now by filtering out the harmonics, we can recalculate. So here's now showing us our voltage. Here's our current. We multiply them together. This is our power. And if we now use our definitions, our power is still 182 well, now 11, because we've lost a tiny bit of active power. Our apparent power is 187, so much, much closer to our frequency domain. And our reactive power, again, very, very similar now to our reactive from the frequency domain. So we can get the same answer, but what we have to do is just separate those harmonics. And the reason that we need to do that is because, if you like, we have potential in the voltage to create power, but that's unrecognized, unrealized potential, because those harmonics in the current are much lower amplitudes. When you multiply them together, they almost disappear. Now, for those who are interested, we don't necessarily have to use the PSD. There's a really neat mathematical trick in the frequency domain that if we use the cross power spectrum, so now if I take the cross power spectrum of current and voltage, I end up with a complex power spectrum effectively. Now the real part of that is called the co-spectrum. And if I measure the area and the co-spectrum, it actually gives me directly the active power. If I take the imaginary part of that, that's called the quadrature spectrum, and I work the area out under that, that now gives me the reactive power directly. And you'll notice again that these are the same numbers we've seen before. So we've essentially got two definitions of power. One, the classical definition, is defined for sine waves. So when you apply a non-sinusoidal function, what it does is it smudges all the frequencies together into one number, and therefore it can overestimate reactive power. But the other one, we keep those frequencies separate in the frequency domain, so therefore when we multiply them together, we end up with a much more robust inference of the reactive power. So in conclusion for this then, there are two time averaging methods because they all involve averaging time in one way or the other. In the time domain, we know that our mean of instantaneous current times voltage gives us active power. We know that the product of RMSs gives us apparent power, and we can calculate Q. And this works really well. It's a pure sine method. But we can still use it in our electric vehicles, providing we stick a filter in that filters out those high-frequency switching harmonics from the fundamental frequency. And anybody who's used Glyphworks will know that's Glyphworks' bread and butter, to put in Butterworth or Fourier filters like that. Now, this method is really good because it can go down to the half-cycle detection. So when you're looking at real-time systems like in eDrive, then the eDrive people have spent a lot of time identifying those half cycles exactly so they can get really good time resolution using this approach. And time resolution is really important with electric vehicles, especially when we're trying to comply with the worldwide harmonized light vehicle test procedure. So again, in Glyphworks and in eDrive, this is a good method, providing we use that filter. Now, the frequency domain method may appear slightly harder, but most of us in Glyphworks are used to frequency domain. By definition, this is a broadband method, so it's our preferred definition of Q. Now, because we're in frequency domain, we have to do a Fourier Transform. So in this case, we tend to have quite big buffers. So we're used to, in Glyphworks land, having 2,048 points in a buffer. Hey, these are going to possibly 1,000,000 points in a buffer, because the buffer has to be sufficiently big to get those low frequency fundamentals in here. So it's not just the high frequency, but we need the low frequency. That means a big buffer. And that is a problem, because now a big buffer takes a lot of time, and therefore it's slower to react. So it's not quite so good for the electric vehicle systems and the worldwide harmonized light vehicle test. So even though you might think, if you know me, that I would naturally favor the frequency domain because I have been for 25 years, in this particular case, I would probably favor the time domain, but I would use a low-pass filter to isolate it. And the reason being, I can get much better time resolution. So with those methods, they're all time averaging. And the best we can possibly get is the average over a half cycle. What happens, though, if you really want to investigate the switching harmonics and things like that? They're a much higher frequency. How do we do that? And that's where the instantaneous methods come in. And again, just like the time ones, I'm going to talk about two domains. So I'm talking about the Clark transform method in the time domain and the Hilbert transform method in the frequency domain. Now, I will warn you that if we brought maths in here, this would be a lot more than high school maths. So instead, I've drawn them as pictures, and I hope you enjoy the pictures, and I hope that they're revealing for you. If anyone wants to follow the maths, give me a ring, and we can go through those, and that will be a most enjoyable afternoon or coffee break for us. So the way these work is a process called direct quadrature transformation. Now that sounds really impressive, so let's go into what direct quadrature transformation is. So first of all, when we digitize data from, say, a three-phase system, so we've got phase A, B, and C, these could be voltages or currents, we've got millions of data points coming in. Now, we as smart engineers know we don't need a million points. If these are sinusoidal, and if they're equal and constant amplitude, and all the phases are equally angular separated, we know that we can actually represent these using just three numbers, really. All we need to know is the amplitude, the sine wave, the initial phase angle, phi, and omega, the rotational frequency. And knowing these three numbers, we can predict exactly what these values are going to be any point in time, because they're just sine waves, really. And we can also draw them using this, what we call a phasor diagram. So we've got the three phases here, and these are rotating around with frequency omega. So at any point in time, we know what the radius of this phase is going to be, that's S, and we can work it out. So this is a polar coordinate system, and smart engineers have been using this for a long time. If we want to use polar coordinates, if I want to estimate, for example, what the power is, knowing the voltage and the current, I can use those polar representations here. So I've got the apparent voltage here, multiplied by cos omega t and the phase of that. And I've got the apparent current, cos omega t times the phase of current. And I know if the current and the voltage phases are the same, the power's wholly active. And if they're not the same, then there's going to be some ratio of active and reactive power. So this is nice and easy. It's the basis that we've done in all the hand calcs. You'll notice these equations are the same as we used in the first set of slides. But it's not very good when you've got digitized data. You've got to know the amplitude, for instance, but you've got normally a million points. It's also very inflexible if we start getting high frequency harmonics. So let's say we've got a higher frequency switching harmonic. So this is spinning round a lot faster than this is spinning round. That gives us horrible double angle formulae. And we remember that they're nonlinear transforms, so they're hard to calculate, and it becomes really complicated too. So how do we get over that and make it simpler? Well, an engineer would say, rather than using polar coordinates, let's use rectangular coordinates instead. So same thing, so still got this phasor rotating here, but this time, rather than measuring it in terms of its radius S, the apparent power, let's measure it in terms of its X component and Y component at each point in time. Now we call these alpha and beta usually, rather than X and Y, but it's just preference. And usually we make use of nice complex number formula, so we'll use the y-axis is the imaginary one. And this is the real power of moving to rectangular coordinates. Because we can use complex number theory, the maths becomes really simple linear maths to do this. So the pros and cons. Well, the cons are it's digital. So it's not just knowing the amplitude, frequency, and phase anymore. You have to know the individual values at each point in time, and you actually need to know alpha and beta, so their X value and their Y value at each point in time. So that's 2 million data points, if you like, for that. But there's certain advantages. It's brilliant for digitized data. You don't have to make any assumptions either. So if the amplitude changes all the time, hey, it doesn't matter. This can change. It's not a circle anymore. It can be any shape you like, and it can evolve with time. They don't have to be equal and constant angular spacing either. And it doesn't even have to have a constant frequency. In fact, sometimes if you've got complex ones, they can be coming backwards and forwards as well. So the phasor can change length with each point. The phase can move backwards and forwards with changing phi. And it's really fast because it's a linear analysis in the complex domain. So now, if I want to calculate the power, then what we do is use complex numbers. So we've now got our voltage here. So this is our complex voltage in terms of alpha and beta. Our complex current in terms of alpha and beta. When we multiply these together as complex numbers, we end up with a real power and an imaginary power. And guess what? The real power, again, is the active power, and the imaginary, just as we saw in the frequency domain before, is the reactive power. So again, if I take the amplitude of those, the modulus, I end up with my apparent power coming in as well. Okay, so it's really quite neat, and you can see how we're getting those same values that we want, that robust active power, that accurate active power, that robust reactive power. The question you're probably asking yourself now is, this sounds really neat, but how do we get those alpha and beta values? And that's where the Clarke and the Hilbert transforms come in. So they both do the same job. They both give us alpha and beta, but one works in the time domain and the other in the frequency domain. So this is the Clarke method in the time domain. Now, Clarke assumes that you've always got three phases. Now, what it's doing is, if I know that I've got three phases, they're all the same amplitude, they're all equally spaced, and they're all sinusoidal, then at any point in time, I can measure all three of those, either voltages or currents, and I end up with an A, a B, and a C. Now, because we know the sine waves, and we know that they're all 120 degrees apart, we don't have to wait until one of them hits a maximum to know its amplitude. At any point in time with these three values, we can predict what that amplitude is going to be. We can also say how far through the phase we are as well. And that's how Clarke's working. So alpha, we can find using this really simple equation that if I take the value at A plus minus half the value at B minus half the value at C, multiply it by 2/3, that tells me the value of alpha at that time. And beta follows this one. And if I want to find out the instantaneous amplitude, all I have to do is take the modulus of alpha and beta. And if you look, you can see that even though these sine waves are going up and down like sine waves do, then what this is doing is it's showing us where the envelope of those are. So at any point in time, I can tell you what the amplitude really is. I don't have to wait until I get a peak. And it can be changing in real time too. So even in this, where we've got this little peak coming out, which is a fraction of a second, we can pick that up using these instantaneous methods. We wouldn't pick that up if we had to wait for a half cycle to evolve. Now, the Hilbert transform does exactly the same job. It's just calculating alpha and beta, but it does it differently. So what this does is it works in the frequency domain, as you'd imagine, really. So we now take our time history. In this case, I've chosen voltage. If we did a Fourier transform of that, then Fourier transforms give us positive and negative frequencies. Now, if I were to set all the negative frequencies to 0 using this H, this Heaviside set function, and then inverse Fourier transform, what I get back is actually a complex time history. And hey presto, the real part's alpha and the imaginary part's beta. So this is actually a really, it sounds like black magic, but it's really fast and really simple to do. And the nice thing with this is you can even give it a single phase. You don't need three phases. And then you can combine the phases using this complex number algebra. And that means we can have any number of phases we want. So next generation electric vehicles with 9-phase motors, no problem at all. We can calculate all of that using this Hilbert transform. And also, it can be suitable for the phases don't have to be balanced. They can be non-sinusoidal waveforms as well, and they can be changing really rapidly as electric vehicles do. So we've got the Clarke transform and the Hilbert, and they both give us the same end goal, alpha and beta. But what's the benefits and the disadvantages of those? So if we look at the Clarke transform, it only works for 3-phase. It has to be sine waves, technically, and it needs to be what we call balanced. So that means it's got to be equal and constant amplitudes in all the phases, and equal angular spacing between the phases. And that really means that we're looking at stationary waves, ones that don't change too quickly. However, the advantages is it's really good for real-time calculations because you can work out those alpha and beta at each point in time. You don't have to keep going backwards and forwards or holding a buffer. It's often used for non-sinusoidal waves, so even though it's supposed to be sinusoidal, we still use it, and there are a number of papers which use it. And again, although it's supposed to be stationary, it does work quite well for non-stationary, and there's even a check to make sure how balanced it is. So a lot of papers which I read, they start off with saying, we're going to investigate non-sinusoidal transient AC signals, and we're going to use a Clark transform. And then they usually add a little caveat that says, now we know this isn't perfect, however, it's good enough. And certainly that's what we've found. We've found that it works very well most of the time, even though we've not got the perfect conditions. Now, in the frequency domain, we've got Hilbert. So it's a more complex analysis. It does require using FFT and their big buffers. And that really makes it a bit unsuitable for real-time calculations. So it's better in the land of GlyphWorks, for instance, than in the land of eDrive, because you have to buffer up a huge quantity of data and then process that data to get your answers. However, the processing itself is wickedly fast, and also it's suitable now for single and multi-phase, non-sinusoidal, transient signals, so everything that we have a disadvantage with Clark becomes an advantage with Hilbert. So how do they compare? Well, these are pure sinusoidal cases here of a three-phase supply. If I calculate my alpha and beta using my Clark and Hilbert, you can see I've overlaid them, and we get identical results of alpha and beta. And of course, if I take the modulus of the alpha, that gives me my instantaneous amplitude. Again, it's a constant straight line, it's perfect. And the modulus of that, the argument, is my instantaneous phase angle. And again, perfect overlay. Both give us identical answers. If I change it for a non-sinusoidal wave, so now in theory we're breaking Clark, but we notice actually that the alpha and beta is not that bad on Clark, which is probably why all the papers have got reasonably useful answers using Clark, even though it's supposed to be substandard. You can see here this is showing us the gamma, this is showing us how balanced it is. And again, if we look at the instantaneous amplitude, there's some ripple in that, but it's not bad. We're getting the same answers, really, Clark and Hilbert, roughly, and same with phase. So Hilbert offers as that potential. Clark's not too bad. You will see there are some differences, and Hilbert's correct and Clark's slightly incorrect, but it's still usable. So let's finish now with some GlyphWorks post-processing and show us using that analysis and what we can do with it. So the first one, we're going to be using some simple analysis. So we're going to use that windowed statistical method, and we're going to calculate the power factors for the fundamental frequency. Remember that half cycle frequency in here. And then we're going to go on, we're going to compare that using the Clark and Hilbert methods to do the same thing. Because even though they're instantaneous methods, when we actually do some smoothing afterwards, we should get the same answer because, they're telling us the same thing, really. And then we're going to take a giant leap and we're going to use the Hilbert to investigate what happens in the inverter switching. So go much higher frequency than the fundamental. So the signal that we're using, so I have my friends from eDrive to thank for digitizing these signals, and especially Mitch Marks, who's helped a lot with developing all of these methods and for testing us out on how to explain them as well. And here we can see some that Mitch has given us. This is our current and this is our voltage from an electric vehicle. I've just zoomed in for part of this so we can see it in more detail. And I've also done the frequency spectrum here. So here we can see, just as we saw before, we can see the fundamental frequency at the low frequency, and we can see these switching harmonics coming in here, and that's due to the inverter switching. And again, as before, we remember we've got the fundamental over here, spectral gap and the switching harmonics. So, if we isolate the fundamental frequency by putting in a low-pass filter, and the low-pass filter I've actually put in just about here. So I put it right in here at around about 5,000 to 6,000 hertz. So I've not put it in low, and the reason for that is Mitch was pointing out we need the harmonics of the fundamental, and so you just need it in a point where you switch out the switching harmonics, but you've still got those high-order fundamental harmonics. And what we end up then is this nice plot here. So this is shown through time. The active power, which is in red, and the blue one here is the apparent power, and the green down here, this is the reactive power. And obviously this is the power factor. And so through this, we can see that we've got some reactive power in here, but for the bulk of it, actually the power factor is quite high. So most of this is actually doing real work, and it's good stuff. Now, if I hadn't have put that filter in, then we would have used that alternate. We would have used the pure sine definition, and that would have predicted that the reactive power was higher than the active power. So that could have been very misleading for us when we're trying to optimize our electric vehicle control system if the reactive power is very sensitive to harmonic switching frequencies. So again, this is really if we don't filter. So always recommend when we're using this to do the filtering, set it quite high to make sure that we chop out those switching harmonics, but we keep in the higher order harmonics of the fundamental. And then we'll get a really good indication of active, reactive power and so on. Now, this is using the Clark transform. So again, we've used two analyses here. The first one is to use a Clark transform, but after we've done it, let's just average out the results so that they're over the half cycle length. And again, we see that this is very, very similar to what we saw on the previous slide. It's hard to compare them because I did them at different scales, unfortunately, but you can see that actually it's about the same, and that's what we'd expect. Now, I can also give the Clark on the unfiltered one, and you'll notice again it carries on being robust because it's not trying to do the average, it's not trying to do that area calc. So here we see that there's slightly more reactive power coming in with all those switching harmonics, but not drastic. It's not dominated it at all. It's only a moderate change. And we can see its effect here probably more pronounced on the apparent power coming in. Of course, we could do the same with Hilbert. And if we do the Hilbert one, so you'll notice, if I just quickly flick between them, you'll notice very little change occurring over here on this plot. The only reason that we got this one jump here is simply because this is about 0 coming in here. And similarly here, if we don't do the smoothing afterwards, again, a very stable representation of the plots. Hilbert's slightly better than Clark, simply because it's a highly non-sinusoidal wave. But again, both of them work quite well. And to finish off, of course, we want to use Hilbert for what it really is intended for, which is going in like a microscope to look at the high frequency. So now, if we don't do any smoothing at all, and there's no filtering, then when we look at the Hilbert transform, it looks all spiky like this, like a hedgehog's gone past through the page. But remember, this is very high frequency. So if we zoom in around this little interesting point here, for example, we can actually start to see at the really high frequency switching harmonics what the active and reactive power is going to be and the power factor. So this is actually shown as the voltage profile here. So we can see the voltage building up as we want to build up the amplitude of this current here. And we can see the instantaneous effects of the active and reactive power due to that switching. So in conclusion, though, we've had a look at, first of all, we've gone back to school, to look at how does sine waves work, how does AC power work. And the whole idea of this is we want to be able to calculate power so that in GlyphWorks we can calculate the efficiency. That's our end goal, so that we can calculate the efficiency and we can optimize that AC inverter and motor control system. That's where we're going with it. Now, we looked at the AC power and we said that in a normal grid, we would be looking at active and reactive. And for our EVs, it's the same things we want to do. The active is consumed. That's the energy needed to drive the vehicle. The reactive isn't consumed, but it causes efficiency losses. So what we actually want is an accurate measurement of active power, because that's the parameter we want to maximize. And we need a robust inference of reactive power, because that's the parameter we want to minimize. And we also looked at definitions for active, reactive, the apparent, and the power factor. And we looked at the analytical, digital definitions, and we also looked at a pure sine wave definition and the broadband one using the Fourier Transform, where we keep the frequencies separate. Now, when we looked at the time averaging methods, so we looked at time averaging instantaneous, the time averaging methods, these are all analysing the fundamental frequency. They're not interested in the switching harmonics, just the fundamental frequency. So in this case, we used a time domain approach, which is the windowed statistical method. This is the same one that eDrive uses internally. So it's a pure sine method, but for EVs, that's not a problem. We can put in a low-pass filter to isolate the fundamental from the switching harmonics, and then it works brilliantly well. And the benefit is we can go right down to the half-cycle resolution. So it's really tight resolution. That makes it ideal for that worldwide harmonized light vehicle test procedure. If we were to do that in the analog domain or the frequency domain, yes, it's a broadband method, which is good, but the resolution's just not there. We'll not get the changes in throttle response and everything else and load right to be able to pick up the power over this dynamic worldwide harmonized light vehicle test. So it looks like it's going to be a good method, but actually the time method works better. So that's available in eDrive, and it's available as well. You can use that approach using GlyphWorks too. We also looked at the instantaneous methods. So these allow us to go into great detail. They're far more robust, and they allow a high frequency right into the switching harmonics. We looked at the Clark transform and the Hilbert. The Clark transform, really good for real-time calculations, but it's got to be three-phase. And a lot of our EVs now, as we're looking at into the crystal balls, they're moving for higher phases. Ideally, it should be sinusoidal balanced and stationary, but we saw that it's actually quite robust and it's still quite useful. And this can be run real time, remember, so there's still a lot going for the Clark method. But when we're in GlyphWorks lands, where it's post-process, the Hilbert one is really the one that stands out. So it might not be real time, but it can be multi-phase, any number of phases, non-sinusoidal, transient dynamic. It works in all cases and can give us all the results. And we can see here a nice little picture of some of the plots that we saw when we were using the GlyphWorks case studies.